Hi and welcome you all for an University LU program. Let us start today's session by solving a square matrix for eigenvalue and eigenvectors. It is actually the continuation of the previous session. What we have done in the last session was we have defined about what is eigenvalue and what is eigenvector and how do we find the methodology to find eigenvalue and eigenvector for any square matrix. So what we have done in the previous session is a problem where we add non-repeated roots, non-repeated eigenvalues. Here again, I am continuing the same topic, whereas here the roots are repeated. So I've given a question where I've given a square matrix where we are going to find the eigenvalue and eigenvector for this matrix. So let us start. So whereas we can also recall the methodology to find the eigenvalue and eigenvectors. What could be the steps we can list out? Number one, you have to find what is a characteristic equation. How do you find the characteristic equation is by assuming the characteristic equation as lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. Do you all remember what is that s1, s2, s3 is? S1 is sum of the leading diagonal elements of any square matrix, and S2 is you have to sum up all the minor matrix of the corresponding leading diagonal elements, and S3 is determinant of A. So by finding all this S1, S2, S3 and substituting in the assumed form of characteristic equation, we could able to get what is the characteristic equation of the corresponding matrix. Then solving off the corresponding characteristic equation, we'll get roots, or we are going to name it as eigenvalues. So for each of the eigenvalue there exists a corresponding vector, that is by modulus of a minus lambda I of x is equal to 0, where the capital X is nothing but the vector which is a column vector. So through this we can find the vector for the corresponding values. Solving off a 3 cross 3 matrix, we will be getting 3 eigenvalues and the corresponding 3 eigenvectors. So let us begin the session today. So this is a square matrix where the entries of the matrix are 2, 2, 1, 1, 3, 1 and 1, 2, 2. Let us begin the steps to find the eigenvalue and eigenvector. So here we are going to find eigenvalues and eigenvector for this problem. That is, what could be the first step is we need to find characteristic equation to get the eigenvalues. So what is a characteristic equation? Takes a form characteristic, in short I'll write it like this. Characteristic equation takes a form lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. Let us find what is s1, s2 and s3. S1 is sum of the leading diagonal elements, that is 2. Second leading diagonal element is 3 and the last leading diagonal element is 2. So you will get 2 plus 3, 5 plus 2, it is 7. Let us find S2. S2 is sum of leading diagonal elements of the minor matrix. So if you want to get the minor matrix of the first leading element, the corresponding column and the row you have to neglect, and the remaining you can give it as a minor matrix. So this is the minor matrix of the first leading diagonal element. The second leading diagonal element is 3. The corresponding row and the column, if you take off, you will get 2, 1, 1, 2, which is the submatrix of the second leading diagonal element. Similarly, the other minor matrix is 2, 2, 1, 3. So let us find the determinant and sum it up. 3 2s are 6 minus 2 plus 4 minus 1 plus 6 minus 2. So you get 4 plus 3 plus 4, which is 8, 11. Okay. we also find S3. S3 is that nothing but determinant of the matrix. If we take this matrix A, then it is determinant of A is S3. Let us find the determinant 2 into the corresponding row and column. If you neglect, you will get this. The determinant of this is 3 2s are 6 minus 2 minus 2 into the corresponding row and column. If you neglect, you will get 2 minus 1 plus 1 into 2 minus 3. So solving this, you get 2 into 4 minus 2 minus 1. So 8 minus 2 minus 3, you get 5. So as we substitute here, you will get lambda 1 cube minus 7 lambda square plus 11 lambda minus 5 is equal to 0. Let us use next sheet. So the characteristic equation of the square matrix A is lambda cube minus S1 lambda square plus S2 lambda minus S3 is equal to 0. What is that? Lambda cube minus 7 lambda square plus 11 lambda minus 5 is equal to 0. This is the characteristic equation. Now what could be the second step is we need to get the roots or the eigenvalues of the square matrix or eigenvalues of the square matrix through the characteristic equation. So being a cubic equation, the first root you have to find it through trial and error method or by synthetic division. So let us try some values for lambda. Why don't we try with 1? So as we try with 1, you get 1 minus 7 plus 11 minus 5 is equal to 0. So 1 minus 7 minus 6 plus 11, you get plus 5 minus 5 is equal to 0. So lambda equal to 1 is one of the root of the equation, or it is one of the eigenvalue. Now using this by synthetic division, getting the coefficient of lambda cube, that is 1, coefficient of lambda square, that is minus 7. Be careful that along with the signs you need to carry it. If you leave off the signs, then it won't be solvable. 11 and minus 5. So we start with 0. Adding this, you get 1. The root of the first root of this equation, what we found by trial and error method is 1. So let us start with 1. So this is my root 1. Okay. So adding this, you will get 1. Multiplying this, you will get 1. Adding this, you will get minus 6. I hope that all of you are familiar with the synthetic division method. So multiplying this, you will get minus 6. Adding this, you will get 5. Multiplying, you get 5. Adding this, you will get 0. So now the cubic equation is reduced into quadratic. Now this will be lambda square minus 6 lambda plus 5 is equal to 0. On solving this, you have the roots as lambda square minus 5 lambda minus lambda plus 5 is equal to 0. You can split it like this. In this case, the roots are lambda minus 5 and lambda minus 1, the factors. Therefore, lambda is equal to 1, 1 and 5 are the eigenvalues. Are the eigenvalues of the square matrix A. Now what we could observe from this eigenvalue is it is 1, 1 and 5. What we have done in the previous session, it is like we add not repeated roots. So roots would not be repeated for the previous problem what we have done in the last session, and here it is repeated. You could find the two of the eigenvalues, or it is 1 and 1. So it is repeated here. So there are cases like eigenvalues may be repeated or non-repeated. So already we have done problem with the not repeated. Let's see how we are going to find the eigenvector in case if the values are repeated. Now, third step is to find eigenvector. Third step is to find eigenvector. How do you find eigenvector? by finding a minus lambda I of, by forming a minus lambda I of x is equal to 0. A is the matrix, lambda is eigenvalue, I is identity matrix of same order, and x is the vector. It's a column vector. So let us write what is the matrix A. It is 2, 2, 1, 1, 3, 1, 1, 2, 2. Let me check whether I have written the matrix elements 1, 2, 2, 1. Yeah, 1, 2, 2. That's right. Then minus lambda into identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1 of x is x1, x2. So if the order of the square matrix is 3, you can have entries of the column vector as 3. It is equal to 0, 0, 0. Now further, this is 2 minus lambda. When you subtract this, you will get this is 2, 1, 1, 3 minus lambda, 1, 1, 2, 2 minus lambda of x1, x2, x3 equal to 0, 0, 0. We name this as 1. Now, in the place of lambda, we are going to substitute all the 3 eigenvalues, and by substituting this will be a matrix form, and then as we multiply into a column vector, you could produce some equation, but 3 equations with 3 different unknowns you will be able to get it, and solving off we could produce the corresponding vector for this each lambdas. So let us go on with cases taking lambda is equal to 1. Let us take this as lambda 1. Lambda equal to 1. So since it is case 1 and the first eigenvalue, I name it as lambda 1. And substitute lambda 1 is equal to 1 in first equation. So what will you be able to get it? Actually it is 2 minus lambda, so you will get 1, 2, 1, 1. Here you are supposed to have 3. So 3 minus lambda is 2, 1, 1, 2. You are supposed to be 2 minus lambda, so it is 1. So this will be the thing. This is the matrix where you substitute lambda in the previous. So as you substitute here, lambda is equal to 1, you get 2 minus 1, 1. 3 minus lambda 2, 2 minus 1, 3 minus 1, 1, 2 minus 1, you get 1 here. So as we substituted lambda is equal to 1, this is what I am writing in the next sheet. So this is a reduced form, multiplying with the column vector, which is equal to 0, 0, 0. Now we have to take this in terms of equation. Now what we could observe from this matrix is all the 3 rows are same. All the 3 rows are identical. Looking at it, we could see all the 3 rows of this matrix after we substitute lambda 1 is equal to 1. We get all the 3 rows are identical. So putting it in equation form, all the 3 equations will be identical. So in case if you have all the 3 equations are same or identical, we can write that equation as one equation. So I am going to write it as x1 plus 2x2 plus x3 is equal to 0. So all the 3 rows are same, all leading to all the 3 equations are same, that is identical. Therefore I am writing it as one equation. So x1 plus 2x2 plus x3 is equal to 0. Hope that you understand. If you write the other 2 equations in terms, the other 2 equation is also going to be the same. So let us, as we solve this equation, we should be able to get x1, x2, x3. Now how to solve this equation with 3 variables, whereas we have only one equation? And looking at the right hand side, we say it is equal to 0. It is not to some constant. We have it is equal to 0. Now x1, x2, x3, we have 3 variables. Now to solve it by to get the values of x1, x2, x3, let us take some, randomly we take some variable value as 0. Since we are left out with only one equation, there are no other equations to simultaneously solve with this particular equation or to apply cross rule method. Whereas here it is left out with only one equation that has to be solved to get 3 unknowns. So I am taking the value of, randomly I can take any value x1, x2 or x3 as 0. By making this x1 as 0, the equation will be reduced to 2x2 plus x3 is equal to 0. Only by making any of the variable as 0, I could be able to solve this equation. Else it is left out with only one, whereas we cannot solve to find 3 variables. So as we do it like this is reduced into 2 variables. Now we can equate one with the other and we can get all the 3 variable values. It is minus of x3, or this is x2 by minus 1, or this is x3 by 2. Now what is your capital X1 is? Value which we assume for small x1 is 0, and out of which we get x2, small x2 is minus 1, and out of which we get small x3 is 2. So this will be the eigenvector for the corresponding value 1. Similarly, as we go with the next case, case 2. Now what is the second eigenvalue? That is, again here in this case it is repeated. Even though it is lambda 2, it is repeated, the value is same. So you will be left out with same identical 3 equations, whereas as you substitute lambda here in this first equation, you will be left out with same matrix which is multiplied with a column vector will produce 3 identical equations, whereas if it is 3 identical equations, we will consider that as 1. So this could be our equation as a result. You will get x1 plus 2x2 plus x3 is equal to 0. What was in the previous case we have discussed? We randomly assumed x1 as 0. Here we can assume x3 as 0 or x2 as 0. The earlier one we have assumed already x1 as 0, so we cannot repeat it. Therefore, let us assume, or let us take x2 as 0, or you can even take x3 as 0. As we take x2 as 0, this equation will be reduced into x1 plus x3 is equal to 0. Now equating, x2 will be equal to minus x3, or x2 is equal to x2 by minus 1, x3 by 1. So your capital x2, you can very well write it as 1, 0, 1. Maybe this minus 1 or this minus 1. Both we cannot give it as minus. So this will be your capital X2. Now you can see we have produced a unique eigenvector even though the eigenvalues are same. Even though the values are repeated, we could find a unique vector for the values. Let us do case 3. Here, when, what is the third eigenvalue? It is lambda is equal to 5. So we name it as lambda 3 is equal to 5. So as we substitute in first equation, so it is, what is the first equation? It was 2 minus lambda, 2, 1, 1, 3 minus lambda. So it will be 2 minus 5, 3 minus 5, 2 minus 5. So what do we get here? 2 minus 5 is going to be 3. Already it is 2 here. No changes with the rest of the entries except the diagonal elements. So it is 1, 1, 2 minus, it is 3 minus 5. So it is 2, minus 3, minus 2, 1, and it is 1, 2, 2 minus 5, it is minus 3. x1, x2, x3 is equal to 0, 0, 0. Let us work finding it. Minus 3x1. As we put that in equation form, it is first row into this column. Multiply this. So minus 3x1 plus 2x2 plus x3 is equal to 0. The next equation will be x1 minus 2x2 plus x3 is equal to 0. 3 minus lambda 1, 1. Okay. And the third equation is x1 plus 2x2 minus 3x3 is equal to 0. Now looking at these three equations, all the three rows are unique. I mean all the three rows, none of the rows you can find to be identical. Here it is minus 3, 2, 1, here it is 1, minus 2, 1, here it is 1, 2, minus 3. So you don't find any two rows to be identical, whereas left out with all the three equations to be different. Left out with all the three equations different. Whereas in the previous case we found three equations are same, so we wrote one equation, whereas here it is different. Now how do we find the values of this three values x1, x2, x3, small x1, x2, x3 is by solving these three equations. Okay. So whereas we have learnt in the previous class by cross rule, previous session, by cross rule multiplication we can solve to find the values of small x1, x2 and x3. Let us do cross rule multiplication. So for cross rule multiplication you can take any two equations from this. Any two equations is enough to do cross rule multiplication. So let us take the first two. Here we name this S2 and let us name this S3. So from 2 and 4 we can do it. So let us take 2 and 4, or you can also take 3 and 4, or you can also take 2 and 4, any two equations. So what do we do in cross rule multiplication? First let us collect, always we do collect the coefficients of x2, x3, x1, and we finally also end up with x2. Collecting the coefficient of x2 in the two equations, what we have assumed, that is 2 and 3, it is 2 minus 2, and x3 is 1, 1. This is minus 3, 1. This will be 2 minus 2. Now how do we find the values is, working out the determinant of x2, x3, we get x1, that is x2, x3. Working for x2, x3, so x2, x3 will give you x1. Getting the determinant of x3, x1 you get x2, and working the determinant of x1, x2 you get x3. So let us find the determinant of this. x2, x3 is 2, 1, minus 2, 1, and determinant of this could be x1, you can get it from determinant of coefficients from x2 and x3. 2, 1, minus 2, 1, and for x2 it is 1, minus 3, 1, 1, determinant of this, and for x3 it is minus 3, 2, 1, minus 2. So as we find the determinant, it is 2 into 1, 2, minus into minus plus, so it is 2 minus into minus plus So 2 into 1, that is over 2 plus 2, that's 4. You are finding the determinant 1 plus 3, and for x3 it is for x3 it is 6 minus 2. So the reduced form is x1 is 4, x2 is 4, and x3 is also 4. So what is your capital? X3 is 4, 4, 4. You can also very well write this as 1, 1, 1, since the eigenvectors, it is throughout it is divisible by 4. Throughout it is divisible by 4. So we can also write it as 1, 1, 1. So what are the 3 eigenvalues, and the vectors are lambda 1 is equal to 1, and the corresponding vector capital X1 is, as we assume this is 0, we get this as 1 and this will be minus 2. And when lambda 2 is equal to 1, we get the vector, the corresponding vector for this eigenvalue is minus 1, 0, 1. And when lambda 3 is equal to 5, we were able to get the vector. We name this is x1, x2, and this is x3. We get it as 1, 1, 1. So this is the way we find the eigenvalue and eigenvector. Now here, what is that we have studied? Something new added to the previous session is the roots are repeated. When the roots are repeated, and if we come out with 3 identical equations or any 2 identical equations, we assume that identical equation, that is 1. The number of identical equations, you take it as 1, and then through that you have to solve and get the eigenvectors. So now, as we have done a problem in a previous session, and we have done one more in this session, so let us, and anyway in the rest of the topics in this unit we will be doing diagonalization and by similarity transformation and by orthogonal transformation. Anyway, we will be finding eigenvalue and eigenvectors. So let us continue with the next topic. We have a break, that Cayley-Hamilton theorem. Okay, we have a break in the continuation of the topics. Like Cayley-Hamilton theorem will not be exactly finding the eigenvalue and eigenvectors. There you can find something different. So as a break of the entire unit as a stretch, we will do the Cayley-Hamilton theorem as a next topic, and then we continue again with eigenvalue, eigenvectors, where a symmetric matrix would also be taken for diagonalization and quadratic form conversion, quadratic form to canonical form conversion. And here we have some properties of eigenvalue and eigenvectors to be discussed, whereas these properties related problems could also be asked for 2 marks, which is important in 2 marks. Property related problems could be asked for 2 marks. So let us discuss the properties of eigenvalue and eigenvectors in short, and we'll do some 2-3 problems, and then let us continue with the Cayley-Hamilton theorem. Properties of eigenvalue and eigenvector. Here in this worksheet, I have typed all the properties of eigenvalue and eigenvector, so it will be easy for us to recall and discuss about it. What is the first property? Is there are some 10 to 12 properties. As we list out, it comes around to number 12. What is the first property? Is sum of the eigenvalues of a square matrix equals to sum of the elements of a leading diagonal elements. What is a leading diagonal elements for any matrix? If you sum up, and that sum will be equal to the eigenvalue sum. So sum of eigenvalues would be equal to sum of the leading diagonal elements as the first property. And second property is product of the eigenvalues lambda 1, lambda 2, lambda 3. So that will be the product. So the product of the eigenvalues for any square matrix will be equal to determinant of A. You can very well find determinant of A for any matrix. So this would be always equal. That's the second property. And third property is if A be a square matrix of order n and A transpose have the same eigenvalues, A transpose will have the same eigenvalues. If this lambda 1, lambda 2, lambda 3 are eigenvalues, then A transpose eigenvalues will also be lambda 1, lambda 1 transpose, lambda 2 transpose, lambda 3 transpose. That would also be same. And the fourth property is eigenvalues of a triangular matrix. Eigenvalues of a triangular matrix, it means as well as upper triangular and lower triangular. In that case, you can say the leading diagonal elements are nothing but the eigenvalues. Triangular matrix in such case where we also say upper triangular and lower triangular. Upper triangular matrix, in that even in upper triangular matrix we have the leading diagonal elements are the eigenvalues, or with lower triangular matrix also the leading diagonal elements are just the eigenvalues. If lambda is eigen, the next property, if lambda is eigenvalue of A, if we call lambda as eigenvalue of A, then this K is some constant which is not equal to 0. Then this K lambda is the eigenvalue of Ka, some multiplier, some constant multiplier. When you multiply with this lambda, when you this K would be the multiplier of lambda if the matrix is multiplied with the same K, where K should not be equal to 0 is some scalar. So if you know A, if you know the eigenvalues of a square matrix A, then we can get the eigenvalues of 2A, 3A, 4A or something like that, etc. Okay. And the next property is if lambda is eigenvalue of A, then lambda power n is eigenvalue of A power n. And look at the last line where n is a positive integer. Where n is a positive integer. So if we take A power 1, it is nothing but A. If we take A power 2, that is A square. In case of to find the eigenvalue of A square, it means it is enough if you find lambda square. That is lambda 1, lambda 2, lambda 3. If it is eigenvalue of A, then lambda 1 square, lambda 2 square, lambda 3 square will be the eigenvalue of A square. And similarly like A3, it is A cube, A power 4, like that. So if you have to find the eigenvalues A power 4, you no need to find what is the matrix A power 4, but finding the eigenvalues of A, you can also give it for eigenvalues of A power 4 by just squaring, cubing and taking to higher powers. That's the next property. And the next one is lambda's, if lambda's eigenvalue of a non-singular matrix. What is a non-singular matrix? All these types of matrices we already discussed. What could be the non-singular matrices? Where the determinant of A of any square matrix should not be equal to 0. So that is a non-singular matrix. So a type of matrix where if lambda is eigenvalue, then 1 by lambda will be the eigenvalue of A inverse. When do we can define A inverse? Only if a matrix is a non-singular matrix. So in that case, A inverse eigenvalue would be 1 by lambda, provided the matrix A is a non-singular. The same property is if it is A transpose, then lambda value of A transpose is also 1 by lambda, provided the matrix is an orthogonal matrix. Here it is non-singular and here you can very well see it is orthogonal matrix. And the ninth property is if you have to find what is the eigenvalue of A minus Ki, A minus 2i or A square minus 2i, in that case it is enough if you know the eigenvalue of lambda, and knowing the eigenvalue of lambda, if you subtract with that scalar lambda minus k, that is enough. We can get the eigenvalue of A minus Ki. K could be a constant value. For any constant value, you can find lambda minus ki will be the eigenvalue. Then, so as we have discussed this in the fourth property already, upper or lower triangular matrix is equal to the elements in the leading diagonal elements. So the leading diagonal elements of any matrix will be leading diagonal elements of any matrix, in case the matrix should be upper or lower triangular, will be the eigenvalues. The next property is eigenvalues of a real symmetric matrix. Eigenvalues of the elements are real, symmetric matrix are real. This is of course the real symmetric matrix eigenvalues would be definitely real. And the last property is eigenvalue of an idempotent matrix are either 0 or 1. What do you mean by idempotent matrix? When you can say a matrix A square is equal to A, then that matrix you can call it as idempotent matrix. So matrix of that kind, eigenvalues would be always either 0 or 1. So these are the 12 properties where will help us to find the values and vectors of any problem that can be defined easily. If we know the matrix of A, we can generalize for A square, A power n, A minus ki, and A transpose, A inverse, like that. I have listed some properties too. Listed some problems. If the sum of two eigenvalues and if the sum of the two eigenvalues and trace of a 3 cross 3 matrix A are equal to trace of a 3 cross 3 matrix A are equal to trace of A, then find lambda A is actually equal to trace of the matrix 3 cross A, then find determinant of A. They say it is just sum of two eigenvalues and trace of 3 cross 3 matrix are equal. So let us write this. So using these two we have to find determinant of A. This minimize. Trace sum of two eigenvalue. Let us take lambda 1 and lambda 2 are two eigenvalues. Sum of this is what? Lambda 1 plus lambda 2 is equal to trace of a 3 cross 3 matrix. What do you mean by trace of a 3 cross 3 matrix? It is nothing but sum of eigenvalues. Sum of trace of a 3 cross 3 matrix is the leading diagonal elements. Sum of the leading diagonal elements. How do you get the sum of the leading diagonal elements? Sum of the leading diagonal elements is nothing but sum of the eigenvalue. That's the first property. Sum of the leading diagonal elements is nothing but sum of the eigenvalues. So as by the property, you can write trace of 3 cross 3 matrix is lambda 1, lambda 2, lambda 3. So this is lambda 1 plus lambda 2. Okay. Now, through this we have to find what is determinant of A is. So what is determinant of A? Determinant of A is nothing but finding, as by the property you can find the determinant of A by drawing the product of the eigenvalues lambda 1 into lambda 2, lambda 3. So we know that lambda 1, lambda 2 is the trace of the is equal to trace of the matrix, and lambda 3 is unknown. So if we know what is lambda 3, we can find determinant of A. So can we, from this equivalence, could you able to find lambda 3 is? Yes, of course. So lambda 1, lambda 2 goes off. Your lambda 3 would be equal to 0. Even though we don't know what is lambda 1 and lambda 2, from this relation what is given in the question, it means sum of the two eigenvalues equal to trace of 3 cross 3 matrix, which gives you lambda 3 is equal to 0. Whereas by substituting this lambda 3 value, that is lambda 1 we don't know, lambda 2 we don't know what is exactly, but we know what is lambda 3, that is 0. It means the determinant of A value is 0. So this is the answer for the first problem. So we were able to find what is determinant of A is. What is the second problem is the product of two eigenvalue of the matrix. Product of two eigenvalue of a matrix. What is the property which relates to product of the eigenvalue? Product of the eigenvalue is nothing but equal to determinant of A. We just now used it in the previous problem. Using that, we can find what is the third eigenvalue of A is. Now they very well say product of two eigenvalue, not three. Product of two eigenvalue of a matrix is equal to this is 16. Okay, product of two eigenvalue matrix of this matrix is 16. Find third eigenvalue. Knowing the product of 2, that is 16, we are supposed to get third eigenvalue. So let us work this. Product of two eigenvalue. Product of lambda 1 and lambda 2. That is lambda 1 into lambda 2 is 16. Knowing this, we have to get a third eigenvalue. Knowing this, we have to get what is the third eigenvalue. How are we going to get the third eigenvalue? The product of the eigenvalue lambda 1, lambda 2, lambda 3 is nothing but equal to determinant of A. This is by the properties of eigenvalue and eigenvector. So let us find determinant of A is from the matrix. Let us find determinant of A from the matrix. Let us write what is matrix A. What is the matrix A? It is 6 minus 2, 2. 6 minus 2, 2. 2, 3, 1, 6 minus 2, 2, 2, 3, 1. Minus 2, 2, minus 2, minus 2, 3, 1. So 2 minus 1, 3. 2 minus 1, 3. 2 minus 1, 3. So let us find the determinant of A. So as we find determinant of A, we get 6 into 9 minus 1 plus 2. 9 minus 1. Minus into minus plus. Minus 1 plus 2 into 2 minus 6. So we get 6 into 8 plus 2 into 8 plus 2 into minus 4. So as of you get 48 plus 16 minus 8. 9 minus 1, let us cross check, plus 2, it is 9 minus 1 plus 2 into 2, the corresponding row and column, it is 2 minus 6. Yeah, we get 48 plus 16 minus 8. So it is going to be 56. So 6 minus 2, let us cross check with the matrix. 6 minus 2, 2, minus 2, 3, 1, 2 minus 1, 3. 2 minus 1, 3, 6 minus 2. 6 minus 2. Okay. It is 56 here. So as we substitute this lambda 1, lambda 2 is 16. Lambda 3 is equal to 52. 56, it's 56. So as we substitute in the place of lambda 1, lambda 2 is 16, lambda 3 we don't know what is exactly, it is equal to determinant of A, we found that is 56. So as we multiply, as we bring this 16 this side, your lambda 3 is equal to 56 by 16. So what is lambda 3? What will be lambda 3 is? So lambda 3 is 56 by 16. So this is 4 times of 1, 4. So you get 7 by 2. This lambda 3. So that was a question to find the third eigenvalue. So the third eigenvalue is lambda 3, the 7 by 2. There's one more question which I've given it here. Like 1 and 2 are eigenvalues of a 2 cross 2 matrix. Earlier what we have done for both the problem, the 1 and 2 problem, was with 3 cross 2 matrix. Here it is with 2 cross 2 matrix A. What are the eigenvalues of 2A squared and A inverse? If 1 and 2 are only 2 eigenvalues, if it is 2 cross 2 matrix, I have given the eigenvalues. We are about to find what are the eigenvalues of 2A square and A inverse. The third problem, the eigenvalue is 1 and 2 of a 2 cross 2 matrix. So there were only 2 eigenvalues. I know what are the eigenvalues, and these are eigenvalues of the matrix A. So we are about to find what is A square and 2. We are about to find the matrix of 2A square and A inverse. A square and A inverse 2A square and it was A inverse. Is A inverse. Okay. So what was the property we have related to this? We have learnt, if we know the eigenvalue of A, then A power n eigenvalue, to find the eigenvalue of A power n, so it means like lambda power n will be the eigenvalue of A power n, and lambda 1 by lambda will be the eigenvalue of A inverse and A transpose. These are the two properties we have learned. So using these properties, we can give the eigenvalues of 2A square and A inverse. So eigenvalue of A, the eigenvalue of A is 1 and 2. Not. An eigenvalue of A square is 1 square, 2 square. An eigenvalue of 2A square is 2 into 1 square and 2 into 2 square. So that is 2 and 4 2s are 8 are the eigenvalues of 2A square. And what will be the eigenvalue of A inverse? If lambda is the eigenvalue of A, then lambda inverse will be the eigenvalue of A inverse. So if one eigenvalues of A is 1, 2, eigenvalue of A inverse will be 1 by 1 and 1 by 2, which is 1 and half. So this is a way we have to do we have to find the eigenvalues related to the eigenvalue and eigenvector properties. We can list out many more problems, but as we have time constraints, I've listed some three different problems for you. So this is the way we have to apply the property. So here and there, if we could code the property and then proceed, what is that we have done? then proceed what is exactly, it will be easy for us to understand. So it is lambda A inverse. Lambda per n will be the eigenvalue of A. It is 1 by lambda. So we have to state the property. Here we can quote what is the property is. Here we can quote what is the property is. So like this, as we quote the property and we could do the problem, it will be easy for us and we will understand better. So we were doing we were finding what is eigenvalue and eigenvectors for different roots, for repeated and not repeated roots, and we had discussed about the properties, about 12 properties, in short. If you have to recall, we can say the sum of the eigenvalues. So I just recall sum of the eigenvalues, lambda 1 plus lambda 2 plus lambda 3 is equal to trace of the matrix, or that is leading, sum of leading diagonal elements, leading diagonal elements, leading diagonal elements of matrix A. This is the first property. And the second one, product, lambda 1, lambda 2, lambda 3 is equal to determinant of A. And if lambda is the eigenvalue of, A of a square matrix, then you can say 1 by lambda is the eigenvalue of A inverse, provided A is non-singular matrix. And you can give this as A transpose. 1 by lambda will be the eigenvalue of A transpose, provided your A is orthogonal matrix. What is orthogonal condition? When you can call a matrix to be orthogonal matrix? Only when A transpose is equal to 1. A transpose equal to I. In that case, we can call this matrix here as orthogonal. Here, if lambda is the eigenvalue of, A, then lambda power n will be the eigenvalue of A power n. Then if lambda is eigenvalue of A, then K lambda will be the eigenvalue of K. So like this we can add on. And eigenvalues leading, next property. I have clubbed all the properties 3, 4 and the last two properties together, so all that put together we have given some. And the next is leading diagonal elements of triangular matrix. Triangular matrix, in case this is upper or lower triangular. In that case, the eigenvalues, this is nothing but the eigenvalues of A. In case a matrix is a triangular matrix, either it is upper triangular or lower triangular matrix, then the leading diagonal elements would be nothing but the eigenvalue of A. And the eigenvalues of a real symmetric matrix are real. Eigenvalues of a real symmetric matrix are real. This is about eigenvalues. Eigenvalues of a real symmetric matrix are real. And idempotent matrix, in case your matrix is an idempotent matrix, then the eigenvalues will be either 0 or 1. So consolidating all the properties together, I've just recalled. So as you state the property and do the problem, it would be better and it would be apt to for 2 marks. So instead of solving the entire matrix for using characteristic equation and then solving the characteristic equation to get the roots, here and there we can quote the properties and we can make it make the problem and we can solve the problem simply as such. Yes. So we can now move on to the next topic, that is Cayley-Hamilton theorem. Cayley-Hamilton theorem would be, there's a statement where you can state what is Cayley-Hamilton theorem is and what are the major application part of Cayley-Hamilton theorem. So we are going to concentrate on the statement and the application point of it here in this unit, that is Cayley-Hamilton theorem. This being the person who defined, who stated this theorem, so it has been Cayley-Hamilton. What does the statement says? What is the statement is about every square matrix, every square matrix satisfies its own characteristic equation. So it is about just two lines. Every square matrix satisfies its own characteristic equation. What do we mean by this? Is nothing but, how do you find the characteristic equation? Just by finding determinant of A minus lambda I is equal to 0. This is how we find the characteristic equation. So instead of finding this characteristic equation every time, we will assume we take the characteristic equation of the form lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. This is nothing but finding out A minus lambda, determinant of A minus lambda I equal to 0. So as we find this, it means we are finding the characteristic equation. When we say it is equal to 0, then it means it is equal to 0. That's a characteristic equation we find. Now we have discussed this already. Every square matrix. So for every square matrix you can find A minus lambda I, determinant of A minus lambda I, satisfying its own characteristic equation. It should satisfy that it is equal to 0. So it is very simple. The statement of the Cayley-Hamilton theorem, it's very simple. Determinant of A minus lambda I is equal to 0. So this will satisfy for any square matrix. And what is a major, vast application of the Cayley-Hamilton theorem? That is two applications, or we call this as uses or application. We call it as uses or application. One is to find higher powers of A. The other is to find A inverse. Usually how do you find powers of A? You multiply A with another A matrix. In order to find A cube, you multiply A square with A. In order to find A power 4, you can multiply A square with A, or A into A cube into A, like that. Here in this Cayley-Hamilton theorem, using the characteristic equation, we can find the higher powers of A. And similarly, you can also find higher powers, you can find inverse. You can find inverse. It's not higher powers. You can find inverse of A. What is the inverse of A? That is A inverse. How do you find A inverse? A inverse, actually, without defining Cayley-Hamilton theorem or without using the characteristic equation, you will find that is A inverse is equal to 1 by modulus of A into adjoint of A. This is how we will find. So here, using the Cayley-Hamilton theorem, we can easily find higher powers of A and inverse of A, that is A inverse. These are two uses, or we call it as applications of Cayley-Hamilton theorem. Now let us take one square matrix and we check whether the Cayley-Hamilton theorem statement is true, and also we find and we check for the uses also. We find A inverse and higher power for the same matrix. Let us take things together and we will do it in one question. It is 2 prove Cayley-Hamilton theorem and find A inverse and A power 4. So how to prove Cayley-Hamilton theorem and A inverse A power 4 things together. We are going to do it in one matrix where the matrix A is 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2 is the matrix I'm going to take. So matrix where we are going to find, we are going to prove the Cayley-Hamilton theorem. We are going to check whether every square matrix satisfies its own characteristic equation, and we also find A inverse and A power 4. So in order to check whether the Cayley-Hamilton statement is true, we need to first find what is characteristic equation is. So what do we said? Determinant of A minus lambda I is equal to 0. So first we find what is characteristic equation, and then we check whether it satisfies for the matrix. Okay. What is the characteristic equation? Takes a form for a 3 cross 3 matrix, lambda cube minus S1 lambda square plus S2 lambda minus S3 is equal to 0. This is nothing but determinant of A minus lambda I is equal to 0. Now, as we know how to find S1, it is sum of the leading diagonal elements, that is 6, 2 plus 2 plus 2. And S2 is sum of the minor matrix of the leading diagonal elements. What is the sum of the minor matrix? 2 minus 1 minus 1 2 plus 2 1 minus 1 1 2 plus minus, this is 2 it's 2 minus 1 minus 1 2. So what do we get? It is 4 minus 1 plus 4 minus 1 plus 4 minus 1. So 3 plus 3 plus 3, we get 9. So S2 is going to be 9. So let us also find S3, that is determinant of the matrix. 2 into 4 minus 1, 2 into 4 minus 1 plus determinant, it's going to be minus 2 into 4 minus 1, then minus already we have, so minus into minus plus 1, so we get minus 2 plus. So as we remove the corresponding row and column, we get minus 2 minus 2 plus 1, minus 2 plus 1 plus 1. It is plus 1 into determinant of the corresponding row and column. If you take out, we get 1 minus 2. We get 1 minus 2. So let us check what is the sum. is 2 into 3 plus 1 minus 1 plus 1 into minus 1. So it is 6 minus 1 minus 1. We get it as 4. Characteristic equation is lambda cube minus 6 lambda square, 6 lambda square. What is S3 is 9, S2 is 9, so it is plus 9 lambda minus 4 is equal to 0. So this is what actual characteristic equation of the square matrix. So let us replace this lambda by A. So we can write the characteristic equation of the form in terms of A as A cube minus 6A square plus 9A minus 4I is equal to 0. So when we take in the matrix form, 4 into 1 is nothing but 4I is equal to 0. So we need to check whether this A cube minus 6A square plus 9A minus 4 of I times minus 4 of identity matrix I is equal to 0 or not. If it is equal to 0, then we can say the characteristic equation satisfies its own, every square matrix satisfies its own characteristic equation. So you will be able to prove the statement of the Cayley-Hamilton theorem. So let us find A square, A cube, and then we multiply all this. So how do you find A square is by A into A. So the matrix is 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2 into 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2. So I am just writing A twice because A into A only will give you A square. So as we multiply this, we get 4 plus 1 plus 1, that is 6. In here you get 2, so let me write, it is 2 minus the first row with the first column, first row with the second column. So minus 2 minus 1. In the first row with the third column you get 2 minus, it's plus 1 plus 2. So the second row is going to be second row with the first column, minus 2 minus 2 minus 1. And here you get second row with the second column, you get 1 plus 2 plus 1. Second row with the second column, into 1 1, 2 into 2, it is 4. 4 plus 1. In here you get minus 1, minus 2, minus 2. So as we complete the third row, 1, it's 2 plus 1 plus 2. And here what do we get? This row with this column, minus 1, minus 2, minus 1, minus 2. This is minus 2. Here we get 1 plus 1 plus 4. So as we put this, we get A square as 6 minus 5, 6 minus 5 plus 5 minus 5, 6 minus 5, 5 minus 5, 6. This is A square. Now we have to find A cube. Now A cube is A square into A. What is A square? The 6 minus 5, 5, what is a square is 6 minus 5, 5 minus 5, 6 minus 5, 5 minus 5, 6. What is A is 2 minus 1, 1 minus 1. Second row will be 2 minus 1, 1 minus 1, 2. So as we multiply with this A square with B, we will be able to get it what is A cube is. So A cube will be 6 2s are 12 minus 5 is plus 5. First row with the first column, first row with the second column will give you minus 6, minus 6, minus 10, minus 5. The first row with the third column will give you 6 plus 5 plus 10. And here the second row with the first column will give you minus 10, minus 6, minus 5. And here you get plus 5 plus 12 plus 5. And the second row with the third column will give you minus 5, minus 6, minus 10. Here it is 10 minus plus 5 plus 6. Second column 5 minus 5 minus 10 minus 6. And the last entry is 5 plus 5 plus 12. So adding this you get 22 minus 21, 21 minus 21, 22, 21. So your A cube is going to be like this: 22 minus 21, 21 minus 21, 22 minus 21, 21 minus 21, 22. So as we simplify this matrix, adding and subtracting, we get A cube as this. So let us put this in the characteristic equation form. A cube minus 6A square plus 9A minus 4I is equal to 0. What is our A cube? It is 22 minus 21, 21 minus 21, 22 minus 21 it's just 21 minus 21, 22 minus 6 times of A square. What was our A square is minus 6, 6 minus 5, 5. 6 minus 5, 5 minus 5, 6, 5 minus 5. This is 5 minus 5, 6. This is 9 times of multiplying with the matrix A, the original matrix. That is 2 minus 1, 1, minus 1, 2, 1, minus 1, minus 1, 1, 2, minus 4 times of So if your square matrix is 3 cross 3, then the identity matrix what we have to take is should be again a 3 cross 3 matrix. 3 cross 3 identity matrix. So let us check this. So 22 minus 21, 21 minus 21, 22 minus 21, 21 minus 21, 22 minus, what is this? It is, when you multiply this 6 you get 36 minus 30 minus 30 minus 30, it's plus 30, it's minus 30, this is plus 30. Here we have a minus sign, so it is minus minus 30. We are multiplying just 6 with it, so minus 30, 36, 30 minus 30, 30, this is plus 36 plus 9 times of, you get 18 minus 9, 9 minus 9, 18 minus 9 minus 9, 9, 18 plus 4, 0, 0, 0, 4, 0, 0, 0, 4. So we want to check whether this is equal to 0 or not. So 22 minus 36 will give you 16 plus 18 plus 4. So 22, it is minus 36 plus 9i minus 4i minus 6a square plus 9i minus 4i. It is minus, it is minus here, it is not plus, it is minus. Minus, it is minus. So you get 22 minus 16, 22 minus 16 plus 18 minus 4 will give you 0, is actually 36. 22 minus 36 plus 18 plus 4 will give you 0. Minus 21, minus into minus plus 30, then minus 9 plus 0 will give you 0. 21 minus 30 plus 9, 0 will give you 0. So minus 21 plus 30 plus, it's minus 9 minus 0 will give you 0. 22 minus 36 and your plus 18 minus 4 will give you 0. So like this, if you check all the entries, it will be 0. This is nothing but, says in terms of the matrix form, we proved that is a cube minus 6a square plus 9a minus 4i is equal to 0. So it means it satisfies its own characteristic equation. So we have verified Cayley-Hamilton theorem. So the Cayley-Hamilton theorem, the square matrix satisfies its own characteristic equation. We were able to prove this, we were able to find the Cayley-Hamilton statement is true for this matrix. Now, remaining is, let us find A inverse and A power 4 for this matrix. How do you find A inverse? You find, that is a application of the uses of Cayley-Hamilton theorem. How do you find A inverse is? What is a characteristic equation? It is lambda cube. What is a characteristic equation is lambda cube minus 6 lambda square plus 9 lambda minus 4i is equal equal to 0. Now, this in terms of the matrix form, you get a cube minus 6a square minus plus 9a minus 4i is equal to 0. So, as we re-multiply with a inverse to this above equation, we were able to get a inverse of a cube minus 6a square plus 9a minus 4i is equal to 0. Let's see what happens. We get a square minus 6a plus 9i minus 4a inverse is equal to 0. So it is easy to get a inverse. By putting this on the left hand side and taking everything to the right hand side, we were able to get what is A inverse from the Cayley-Hamilton theorem. This is an application where very easily you can find A inverse from the characteristic equation. That is, when you take, it's minus 4A inverse, so this minus A square minus, it becomes plus 6A 9 minus 9i, it's plus, it is minus 9i, or your A inverse is 1 by 4 times of a square minus 6a plus 9i. So in order to find A inverse, it is enough if you find a square minus 6a plus 9i. We have already found what is a square is. What is our a square is? It is 22 minus 21. 22 is 21. 22. I'm sorry. 21 minus 21. 22 minus 21, 22 minus 21 plus 21 minus 21, 22 minus 6 times of A is 2 minus 1, original matrix 1, 1 minus 1, 2 minus 1, 1 minus 1, 2, plus 9 times of I, 1 0 0, 0 1 0, 0 0 1, just 1 by 4 times of, so it is 1 by 4 times of 22 minus 12 plus 9. And the next thing is addition, subtraction. You will do it row by row. Only by the matrix multiplication you do with row into columns. So 22, it's 21 minus 21 minus 21 minus 21 plus 6 plus 0. Here it is 21 minus 6 plus 0. Here it's minus 21 minus 21. It is minus 12. Minus 21 minus plus 6 plus 0. 22 minus 12 plus 9 minus 21 plus 6 plus 0. 21 minus 6 plus 0. Minus 21 plus 6 plus 0. 22 minus 12 plus 9. So the inverse is 1 by 4. 22, as we subtract this you will get 22 minus 12 is going to be 10 plus 9. It's 22 minus 12 minus 1. Here it is minus 21 plus 6, it is 15. 15. Here you get 15. This is minus, this is also minus. Here it is 22. So 90. This is 15 minus this 15 minus 15, 90. Subtract you get 325. So it's plus 9. I'm sorry. So it is just minus 3 to this minus 3. So so this is what your A inverse is. This will be your A inverse. So as we simplify this, A square minus 6A plus 9I, we could get what is A inverse is. So similarly, if we multiply A inverse to this matrix, to this equation, we were able to get what is A inverse. As we start the equation with A cube, if you multiply A to it, we will get what is A power 4 is. Last subdivision which is added to the question is to find A power 4. How to find A power 4? Now pre-multiply A power 4, pre-multiply A to A cube minus 6A square plus 9A minus 4I is equal to 0. So you get A power 4 minus 6A cube plus 9A square minus 4A is equal to 0. So A power 4 is 6A cube plus 9A square minus 4A is equal to 0. It's plus 6A cube minus when you take this to the other side, you will get 6A cube minus 9A square plus 4A is equal to 0. So as we have calculated, already we have calculated what is A cube, A square. So now we are going to multiply with that scalar 6 and 9. So as we simplify that, we were able to get what is A power 4 is. So it is 6A cube minus 9A square plus 4A. It will be A power 4 is, so 6 times of, what is our A cube? Our A cube is 22 minus 21. Is 22 minus 21, 21, 21, 22 minus 21, it's plus 21 minus 21, 22 minus, we'll check the equations, minus 9A square minus 9 times of a square will be 6 minus 5, 5, minus 5, 6, 5, is minus 5, minus plus 5, minus 5, 6, plus 4 times of a is 2 minus 1, 1, minus 1, 2, minus 1, 1 minus 1, 2. It is equal to, let us simplify this. One 32 minus 9 6 are 54 plus 8 and here next thing is going to be, we'll start little before this, leave some, we'll start here so that it will be easy for us to do it. Okay, so it is 132, here it is minus 54 plus 8. So like this we have to solve. We are just going to subtract 9 into this part plus 4 into that part. So 6 into 21 you get 6, 126 minus, here it is plus, here it is minus, 126 plus 9 5s are 45 minus 4, and here it is going to be 126, it's plus 126 minus 45 plus 4. 26 minus 45 plus 4. And here again this is minus 126 plus 45 minus 4. That's minus. So here 132 minus 54 plus 8. You get minus 126 minus 126 minus 126 plus 45 minus 4. And here it is 126 minus 45 plus 4. Minus 126 plus 45 minus 4. 132 minus 54 plus 8. So as we subtract this you get 8, 46, 46. So 132 132 minus 46 is 6. We get 2. The resultant will be your a power 4. So as we subtract this 132 and we add these two, we get 140. 140 minus 54 is going to be 86. 140 minus 54 is going to be 86. And here when you subtract with this you get minus 130. 130 minus 45 is going to be 85. It's minus 85. And here it is plus 85. Here will be minus 130 plus 45 minus 85. This will be 86. 85 minus 85. Sorry, it is not clear, so I am writing it again. Minus 85, 86 minus 85. Second we get 85 minus 85, and this is 86. So So my A power 4 is 86 minus 85. First row is 86 minus 85, 85 minus 85, 86 minus 85, 85, 85, and this is 86. Minus 85, this is minus 85. So this is how we have to find A power 4 using Cayley-Hamilton theorem. So now we have learned two applications of Cayley-Hamilton theorem, and we have also worked problem. One is to find higher powers like A power 4, A power 5, A power 6, etc. So the higher powers of any square matrix we can find, and also you can find A inverse for any square matrix. So these are the two vast uses or applications of Cayley-Hamilton theorem is. And what is the Cayley-Hamilton theorem states? Every square matrix satisfies its own characteristic equation. So let us recall the steps. We were finding the characteristic equation, and as we replace that lambda by A, we get the characteristic equation in terms of matrix, that is A cube in terms of S1 A square and S2 A, and finally the constant I into Z equal to 0. So as we check whether this characteristic equation satisfies, we say the Cayley-Hamilton theorem is verified. And to find A inverse, we have to reduce 1 less than the power of that. So we pre-multiply A inverse to the characteristic equation, and we pre-multiply A to the characteristic equation to find A power 4. So these are the ways to find, these are the methods, and this is how we find A inverse and A power 4. Now we know to do Cayley-Hamilton theorem problems. We know to find eigenvalue and eigenvectors for repeated and non-repeated roots. The next class will continue with diagonalization, and the last topic of this unit will be quadratic form conversion into canonical form. So these are the two topics which is left in this unit to be done. And as of, we have done eigenvalue and eigenvectors and Cayley-Hamilton theorem. So with that, today's session it's getting over. Thank you for patiently listening. Thank you.